I thought we could talk about Shor's algorithm today. So it's a quantum computing algorithm that is famous for its ability to theoretically break some of our crypto systems. So I thought we could talk about the RSA system in brief, what Shor's algorithm would do to it if a really big quantum computer exists. But because quantum computing is not my thing, I've run over to the School of Physics to get some actual expertise.
Yeah, so I'm going to try and tackle this from the quantum perspective and how do we actually implement Shor's algorithm on a quantum computer. And one thing I really want to do is just get away from this nonsense of we have an infinite number of parallel realities and we just magically magic the answer out of nowhere. But before we do that, back to Mike, who's going to talk you through just how Shor's algorithm works with pen and paper, right?
Yep. One of the interesting things about Shor's algorithm is there's essentially a kind of classical computing component first, then a quantum component, and then another classical component. So I'm going to deal with the classical stuff, and then Phil's going to pop back in and talk about the real quantum stuff in a moment. Let's just have a very quick look at the RSA problem of integer factorization and why we would care about that. RSA is perhaps one of the most famous public key or asymmetric cryptography algorithms. It's used on loads and loads of digital signatures and certificates that you see whenever you go on the internet. Broadly, how it works is you sign a message with the private key and then it can be verified using the public key. And that allows you to, for example, prove your identity as a server or sign some code or something along these lines. It's hugely important and it's underpinned by this integer factorization problem. So as long as you can't factor integers really easily, you can't extract the private key given the public key. And that's the thing, the public key is sent out on certificates all the time. You have everyone's public key. What's difficult is getting the private key. The RSA public key has a number in it called n. N is a very, very large semi-prime number, which means it's actually a prime number p multiplied by a prime number q. Now, this n is part of the public key. So this is public. N is part of the numbers that get sent out on digital certificates and things like this as part of many of our internet processes. P and q, these two prime numbers, are secret. And if we can get P and q, then we can derive the private key. And that would be a problem because if you had the private key, you could forge signatures from any website that you had a certificate for, and then you could, pretend to be that website. You could create spoof websites, things like this, right? Phishing attacks, spoof websites, all of this would be much, much easier if you had access to the private key of some server. So we don't want this, right? Unfortunately, Shor's algorithm exists, right? So Shor's algorithm makes this process much, much easier. This normally is very, very difficult. This is the integer factorization problem. So this is the one of taking a very, very large number and finding out which prime numbers multiply together to get to it. When there's only two of them and they're not really easy small ones, this is going to take absolutely ages, right? Hundreds of millions of years probably with decent compute for any realistic key size. So that's a huge problem. The issue is that Shor's finds a really neat way to make this much, much faster. So what Shor's does is it reframes this problem. It says, okay, we can't do this integer factorization. That's too difficult. What we're going to do instead is create a function that loops periodically back to 1. Right? So it starts at 1, then it goes to various different numbers, and then it returns to 1. And we're going to try and measure the period of that function. How long is it? How often does it repeat? And if we can find that, it's actually not that many steps to get back to P and Q. Let's show an example of the beginning of the classical part of Shor's algorithm, the period finding, and then we can jump to the quantum. So you want to find out what P and Q are, and we're not going to try and directly just do integer factorization, which in this case would pretty much involve guessing a bunch of potential P's and Q's and hope you get one. What we're going to do is we're going to pick some A, and we're going to calculate A to the power of R mod n. A can be any number you like. It has to be 2 all the way up to n minus 1. So you pick one at random. Sometimes Shor's algorithm fails for various reasons we might mention. If so, you just pick a new A and you run again. Right? So the exact choice of A is not very important. What we're going to do is we're going to pick some nice small ones because otherwise my maths is going to break very, very quickly. Right? Or we're going to be here for a very long time running square and multiply algorithms. So we're going to use an n of 15 and an A of 2. And we're going to calculate increasing powers of 2, so 2 to the 1, 2 to the 2, 2 to the 3, and we're going to keep doing that, and we're going to see what happens to this function as we go, mod 15, right? And I'm going to kind of move this. I think I'm just going to use a new sheet, because otherwise we're going to have a problem. All right. So 2 to the 0 is 1, right? So we're going to start at 1, right? So 2 to the 0 is 1 mod 15, and I'm going to stop writing mod 15 because otherwise we're again going to be here all day. So 2 to the 1 is 2. No mod 15. That's all great. 2 to the 2 is 4. 2 to the 3, see if you can follow along. This is not testing my maths yet. We're about to get to the bit that tests my maths. Is 8. Right. So now 2 to the 4 is 16, but it's mod 15, so that cycles back round. You take the remainder, that's 1. Right. So that's 1. The next one's actually quite easy. So 2 to the 5 is 1 times 2 is 2 again. Right.
So even though it's mod 15 and we're thinking it would be 16 times 2, which is 32, it still works to just go back to the 1.
Yes, the lovely thing about modular arithmetic, which makes this much more efficient on a computer, and one of the reasons why I would say it's quite popular, is that you can use the reduced modulus version to do all your, they're equivalent, and that means you can save a huge amount of space. Remember that n is typically 2,000 bits, so that mathematics gets very, very hard very quickly, unless you can reduce back into the correct range and go really quickly. So now if we do 2 to the 6, it's going to be 2 times 2 is 4, and then we do 2 to the 7.
I'm spotting a pattern.
And you're spotting a pattern, right? I spotted it too. Good news. Now, this function, if we sort of did a little graph of it, is going to be going 1, 2, 4. So it goes 1, 2, 4, 8, and then back to 1. And it goes like this, right? And you've got this 1 that occurs over and over again. And that is our period R. And it's that the quantum computer finds. And if we have that, it's actually quite easy to extract P and Q. Why would that help? We've massively distracted ourselves from integer factorisation and done a weird exponentiation. We found R, right, which is 1, 2, 3, 4. For this function. So this is a distance of 4, this is also 4. Right? Why is that good? Well, we'll go away from our numbers for a moment and we'll go back to the symbols. So a to the r is congruent to 1 mod n. And in this case, what congruent means essentially is it goes back to 1 mod n.
So it's like an equals but with the mod.
Yeah, because a to the r might be a very big number, but you reduce and you get back to 1, right? So that's a simple way of explaining congruence just for this video. Which means also that a to the r minus 1 is congruent to 0 mod n. Now, if you think about how modular arithmetic works, it's that clock face thing that we've discussed in previous videos. So, you've got a big wheel with n up here, which is 0, 1, 2, all the way around to n minus 1. If you get to 0, what you've done is you've gone around this clock face mod n some number of times and then got back to an exact multiple of n. Because you've ended up, if it wasn't an exact multiple of n, you'd be somewhere else around here. So this means that actually this is equal to some k multiplied by n. Right?
Where's k come from?
K is just a random integer. It's very big. We don't know what it is. We don't really care what it is. Right? We're saying that we've calculated this period. We've gone some number of times around and got back to 1, which means we've gone some multiple of n number of times. Right? So we can now factor this and do some rearranging. We can use the difference of squares approach, right? So a to the r minus 1 can be factored into a to the r over 2 minus 1 multiplied by a to the r over 2 plus 1, right? That's just this split into two factors, and that is equal to k multiples of n, which is also equal to k multiplied by p multiplied by q, because we know that n is p times q, right? We just don't know what they are yet. So there'll be some people thinking, what are you doing, right? Where are you going with this? Well, the answer is that it's now very likely that a to the r over 2 plus 1 shares a factor with n, which means its factor is going to be p or q, right? Its greatest common divisor, right? That's very, very likely. If it's not the case, which happens on occasion, right? Particularly if r is odd, in which case these will be a fraction, and that's a huge problem. We pick a new a and we go again. Right? But if it is the case, then we can just calculate the greatest common divisor of this and n, and p and q will just jump straight out. Right? That's the idea. And so we can try that with our values that we had before. We know that a is 2. What was r? R was 4. right? A was 2, so this is 2 to the 4 over 2 is 2 squared, right? Plus 1, which is 2 times 2 is 4, plus 1 is 5. What is the greatest common divisor of 5 and our n, which was 15? So 5 just pops straight out. What are the factors of n? 15, it's 3 and 5. So we've got one of P and Q, the other one is very easily obtained, right? And so what we've done, by reframing our integer factorisation problem as one of finding the period of a large function, it allows us to use a quantum computer, which happens to be able to find the period of a very large function. So we want to find the period of this large function, right? So this, remember, I've done this for 15 and for 2. Right? In actual fact, A is going to be a 2,000-bit number, N will be a 2 or 4,000-bit number. The only way I could do this is to do A to the 0, A to the 1, A to the 2, and brute force this really, really slowly on a classical computer. That's not going to work. That's where the quantum computing algorithm comes in. Shor's algorithm finds an elegant way of finding that period.
We already know, we have a list of what prime numbers are. Doesn't that massively reduce the search space? We're looking for prime numbers.
No, we don't have a good list of 2,000-bit prime numbers, right? It's easy to tell whether a number is prime because there are primality tests that give you a high confidence that a number is prime, but actually we don't record them pretty much, right? And it's difficult to sort of express how big a 2,000-bit space is, right? Every bit you add doubles the search space, right? So 2,000 bits is an astronaut, it's some 600 digits. There are a lot of 600-digit numbers.
Okay, the quantum, Phil. Where do we start with the quantum?
Before we go anywhere near a qubit, let's focus on a few things Mike said that were really important. And the first thing is periodicity and the fact that Shor's algorithm is all about taking. It's really elegant. Forgetting about quantum mechanics for the time being, but just the classical part of it is really elegant, where we take a factorisation problem and we turn it into a period finding problem. And when physicists hear periodicity or they hear frequency, they really perk up because that's our bread and butter. Everything from, determining positions of atoms in a crystal lattice to the cosmic microwave background. So everything from the atomic, even the subatomic, up to essentially galactic scales or universal scales. And so much of it is about finding out what are the patterns, what are the waves that contribute to these patterns, what are the different components of these patterns. And that all boils down to the magic of somebody called Fourier and a whole area of physics, engineering, tons of physics engineering, and even computer science undergrads will have heard the name Fourier before. Crops up so many different places. So let's look at this zebra crossing as a really simple image. Forget about John, Paul, Ringo and the other one. Sorry, George.
Very important contribution to the
I know, particularly on this album, classic. So what we're going to do is we're just going to look at this band along the bottom because it's a really simple pattern. And what we want to do is, how does a Fourier transform tell us what are the key frequencies that make up that pattern? What we are doing is we are breaking this down, this more complicated pattern, into a sum of sine waves and cosine waves. Just simple functions that oscillate back and forth. The sines and cosines you know from GCSE maths, middle school maths, high school maths, etc. And all we are doing is we're summing them up. We're taking this frequency plus this frequency plus this frequency, certain amount of this, certain amount of this, certain amount of this, and adding them up. The other thing we need to worry about, and this is going to really play into the quantum explanation, is we also need to worry about where the peaks and troughs are. So what we need to worry about is the phase of those waves too, just how those peaks and troughs line up. And that's what phase is all about. We talk about two waves being completely out of phase or completely in phase and everything in between. So on the screen, what we have is the current image, i.e. what we're going to do is we're adding up those components. We're just looking at the first one at the moment. It's pretty damn boring. It's just grey. And what that is the average value of the contrast in the image. That's all it is. And then what we do is we're going to look at the line profile. So we're just going to cut through that image, which is perfectly flat at the moment because it's all just grey. And then we're going to look at the different waves that make up this image. At the moment, we have just one peak in our Fourier spectrum. And what's our Fourier spectrum? So as it's plotted here, each one of these red bars tells us how much of that component we need. And it ranges, as you can see, spatial frequency here just means how many cycles across the image. How many times does this repeat across the image? You can see the links with Shor's. Mike's sitting back there, smiling. It's the same idea of finding the period, finding the frequency, the number of cycles. And so our average contrast, the interesting thing is that's a completely flat function. So you'd ask what its frequency is. It never repeats in time. So its frequency is essentially 0 hertz. It never repeats. So we see a bar here at 0 because that's our average, that's the mean value of the function. What the physicists, what the electrical engineers, perhaps even the computer scientists, I don't know, would call this is the DC level. It's just flat. It's not rippling back and forth. But watch what happens as we add in. We're going to add in something that varies, just has one cycle across the image. Well, still doesn't look anything like a zebra crossing. 2 cycles. There, perhaps something's emerging. And then remember that it's 3 cycles across the image, roughly. When we hit the 3rd cycle, bingo, we get a massive contribution because that 3rd cycle really contributes quite heavily. And in fact, when it comes to Shor and when it comes to the quantum implementation of Shor's algorithm, essentially your job is done here. We've worked out what that repeat pattern is. However, if we add in, that's a fairly boring, if we add in more and more components, building up the Fourier spectrum, you'll see that not only does the height, the amplitude of each one of those components change, but if you watch carefully, the phase also changes because getting those to align is absolutely crucial. You've got to get them to add up in the right places to generate the image. And as we move across, you'll also see what's happening is it's sharpening up. This is also, particularly for the computer scientists, this is JPEGs in action. This is what JPEGs do. They compress the information down in terms of the waves that contribute, the different frequencies that contribute to the image.
So what we're doing here effectively is using waves to create an image. And then we're looking at what those waves are and how they combine to create that image. Is that right?
I would say, yeah, I would even push it further than saying to create an image. We're using waves to create a pattern. And that pattern can be a pattern in space, like an image. It can be a pattern in time, like a musical note. We could do a Fourier transform of that as well and see what the component frequencies are. Or, particularly when it comes to Shor, what we want to know is what are the particular frequencies that build up that particular function that Mike sketched on the paper a few minutes ago. So previously what we did is something called Fourier synthesis, where we took the individual waves, add them up, and at the end the magic happens and you see the image appear. We're doing it the opposite direction now, something called Fourier decomposition, which is the really important one for Shor's algorithm, in that we have that function. That's being calculated, and what we want to know is what's the period of that function. For the n equal of 15 example, we can look at it by eye. If it's 2048 bits or higher, we're not going to be able to pull that period out by eye. So we're coming at it from the other direction. We've got our function, 1248, 1248, 1248. And now we're asking is, what are the waves, what are the Fourier components that we need to build this thing up? Or, particularly in terms of Shor, what are the frequencies we need to build this thing up? So the first one is boring. Right? The first one is our 0 frequency term, or DC term, or average value of the function. And the average value of the function, 1 plus 2 plus 4 plus 8, divided by 4, gives us 3.75, which is why we get this flat line. Again, we're working with a pretty small example here, in terms of n is equal to 15. But what we have is we go from 0 up to 15, which means we have 16 possible slots here. The function repeats 4 times in that 16 slot window. So that means that the period is for the entire function is 4. It repeats 4 times in our window of 16. Right? That's the number we want to get for Shor. And it turns out that when we do the Fourier analysis, k here represents the number of cycles across this window. If we move to a k equal to 1, so that's 1 cycle across the 16 particular slots, we find that it looks like nothing's happened, but that's because there is no contribution. When we do the Fourier analysis, when we work out what waves, what frequencies contribute to making up this function, we find that for k equal to 1, we get nothing. It's pretty boring because for k equal to 2, we get nothing. K equal to 3, we get nothing. But when we hit k equal to 4, notice what happens. We've now added in that wave. We're going to look at this on the big screen. These circles are not doing a great job of falling on the black points. But what they have captured already is what the period is. It's pulled out that period just from this first peak alone. We know already, and for sure that's what we need. If we add in more components, well, we find when we add k equal to 5, again, we don't need any of that. At k equal to 6, we don't need any of that. K equal to 7, we don't need any of that. But when we hit k equal to 8, look what happens to those red circles. They land on the points. So what we found, and which is so important for Shor, is simply by building this up from different waves, all we need to do is, well, we can forget about this term at 0, because we know that's just the average value of the function. What's really important to pull out the period is this first peak that we see in the Fourier spectrum. We've seen how we can build up patterns from just simply by adding up different sine waves. And so much, in fact, I would argue all of quantum mechanics and all of quantum computing, we can reduce to exactly that. It's about adding up waves in just the right way, adding up quantum states in just the right way, which are described by waves. And a key part of that is interference of waves. I'm going to show you a really simple example just to hammer this home. So what we have two waves here on the screen. Let's look at the sum. So the red one is when we add the two together, right? So we get a big result. We've just added those two waves together. Now let's shift the phase. And this is something, got to point out that this is not just something very abstract. This is what quantum computing is all about. It is about controlling the phase of these waves. So as we move one with respect to the other, and as we knock them out of alignment, what you see is when we sum the two of them together, they cancel out. Destructive interference. When they align, constructive interference, destructive interference. And as you can see, it's a continuum between the two. We can control, it's not one or other, it's not binary, it's that we can control that range. By controlling the phase, we can control how these things add up. There's nothing quantum there. This is pure classical physics, wave physics. You can see it. This is not a quantum computer. It's a signal generator and oscilloscope. Nothing more than that. But it's exactly the same mechanism in terms of interference of waves that underpins quantum computers. So let me show you how this really simple idea of adding up waves translates actually into the quantum world and how it translates to a qubit. What is a 0? What is a 1 in a qubit? Again, you've heard this, oh, isn't it amazing? You know, it's like flipping a coin and instead of getting heads or tails, you get a mixture of heads and tails. Isn't that amazing? Isn't that bizarre? No, it's not bizarre. It's called superposition. And when it comes to waves, everywhere in the world around us, it happens all the time. As you're listening to me speak, it's waves interacting, interfering, the different Fourier components adding together in different ways that give you the tone of my awful brogue. That's what you're hearing. That's superposition in action. Every time you listen to a musical instrument, superposition. Every time you see a bloody image, superposition. It's not weird, it's not wacky, and it's not happening in a billion other universes or parallel realities.
I like your brogue.
Thank you, Sean. Question is, how does this constructive, destructive interference, this summing up waves aspect, how does that translate to the quantum world? How does it translate to qubits? Well, if you really want all the gory detail, and there's a lot of gory detail, including all the maths, well, not all the maths, but some of the maths, there's a blog post which Sean will put the link down there or over there or somewhere in the description. And you can go there and feel free to email me at any time if there's any aspect of that you'd like to discuss in more detail. But we're going to take a very simple system, but it's a system that is actually, it's not just a physicist sort of pipe dream. This is how quantum computers are set up and how they work. We're going to think about something called a trapped ion quantum computer. So we take an ion, so a charged atom, and we trap it in space in what's called an ion trap in a very high, ultra-high vacuum and at low temperatures. And what we're going to do is we're going to use two states of that atom to represent our 0 and our 1 for a qubit. What do I mean by state? What a wonderful question. I think many people will be familiar from school of the idea of electron orbitals. We stack up, we have energies, and the ones that are closest to the nucleus are higher, more strongly bound, and then higher, further away, less strongly bound. Got to point out that's a model, right? That's a fiction. That's not how atoms work, but it's an incredibly helpful fiction. And we're going to be using some incredibly helpful models, I hope, to help you see this. But here, if on the fictional aspects, here's our energy level system. Low energy, high energy, 0, 1, right? Thing with quantum mechanics, however, is that we don't have to be in just this. We don't have to consider the system as being just in this state or in this state. It can be in a superposition. And this is telling us how our probability, the brighter it is, the higher the probability of finding the particle there. So we've got our trapped ion. Let's just focus on one trapped ion. We've got two states. We can change the probability for finding the system in this state, finding the ion in this state or this state. And the way we do that, the way we change that probability, is fire microwave pulses. And I mean microwave, like normal sort of microwave pulses like you'd use to heat food. It's the same sort of frequency range in terms of the energy difference here, a few gigahertz. And by applying precisely timed pulses, we can control how much of the system is in the 0 or 1 state. So it can be completely in the 0 state, completely in the 1 state, or somewhere in between. Superposition, how do we know? Well, the way we know is we fire a laser at it. When it's in this state, the number of photons that we see coming back from the ion are much smaller than if it's in this state. So just simply by counting photons, we get a probability. We make our measurement. The important thing is with quantum, however, is that when we make that measurement, we have to start again. We have to start from scratch, set the system up again, and this is, you might have heard this term, collapsing the wave function. That's what we've done. We've made the measurement, and then we start from scratch. Re-prepare the system, measure, re-prepare the system, measure, etc., etc., etc.
So this is why people do things over and over again and then take an average of it?
Exactly. So with quantum computers, that's what you want to do with a quantum process. It's statistical, it's probabilistic. It's not this or this. It's a probability of it being in this state or this state. And those probabilities are absolutely everything. So you actually have to reset the system every time. Last step in trying to bring all of this together, and there's a lot to bring together, is just how the waves that we talked about connect to those quantum levels, and just what's going on when we measure a probability at the quantum level, at the quantum state level. So I'm going to borrow heavily from a certain Richard Feynman. And I could bury you in linear algebra, we could venture off into Hilbert space and multiple universes, etc., and complex numbers, etc. Instead, we're going to work with arrows drawn on vinyl singles and LPs. This one's a classic. There's no one quite like Grandma, backed with Pinocchio. And this one, actually I feel really bad for putting Tipex on it, is the incredible Shirley Bassey. Remember that what we had, I think I'll hold it up like this for the time being, Sean, if that's okay with you. It's all circular. If you think about the sine wave or the cosine wave, it's coming back to the same point. And we can represent that in terms of revolutions. This is called a phasor. And as we spin it round, essentially, if you think about what's happening with that little arrow, it's following a cycle, right? And that's how we can represent how that wave is evolving in time. Even better than that, we can set it up so... Oh, should also point out that Computerphile owes me for it's about £3 on the albums, if that's okay, Sean. So what we can do is we'll use two record players to represent this state and this state. So remember from your high school, middle school, secondary school, A-levels, whatever, physics and science, is that, we have a direct relationship between energy and frequency in quantum mechanics. We have red and blue light, and what's the difference? Well, it's how fast the wave is oscillating back and forth. Similarly, when it comes to these quantum states in the atom, very simple relationship. E is equal to hf, where f is frequency, E is energy, and h is Planck's constant. And so, if we're in a lower energy state, there we go, it spins round relatively slowly. if we're in a higher energy state, spins round faster. Low energy, high energy. Bottom shelf, top shelf. Right? That's one thing. Why have I drawn the arrows? Well, the length of those arrows tell us about the probability of measuring in this state or this state. When we fire, now if we were to do experiment firing the laser and measuring the photons coming back, what we'd find is we've got a 50% superposition of 0 and 1 because the arrow lengths are the same. We've got singles here. When we measure, we will collapse into one state or another. So what we'll find is that, let's say we measure and we find that it's in the one state. What we'll do then is we'll end up with a larger arrow because we've collapsed the quantum measurement into that state. So our arrow is larger. And the length of that arrow, how do we get from the arrows to the probability? Well, we square the length of that arrow. That's it. Why? Well, we don't quite know. And if you really can conclusively tell us why that's the case, you've got a Nobel Prize. It's something that's plagued, it's called the measurement problem, it's an aspect of the measurement problem, that's plagued quantum mechanics from the very early days for over a century now. But from another perspective, this is really quite straightforward. We just look at how arrows rotate round, and they represent our quantum waves. They're spinning. If it's a higher energy quantum wave, then it spins at a faster rate. What we can't get a handle on by itself is if we just measure this state now, this is the only state we have, right? This is the only thing we can get. We will get 100% probability. That length of that arrow is 1, right? So because we've got 100% probability, it can only be in that particular state because that's the only state that we've got. Now, this is what I meant before. If we want to now carry out our quantum calculation, we have to go all the way back to the bloody start, set the system up again, measure, collapse, rinse, repeat, over and over and over and over again. One final piece of the puzzle we need. So we measure by firing a laser at it, and we essentially go how bright, how dark it is. That's our measurement strategy, and that is what's used in trapped ion quantum computers. How do we control whether it's in this state or this state? What we do is we apply a microwave pulse off the right time that allows us to control what's the probability for it to be in this state versus the probability of it being in this state. And we control that just for the right time, then we can literally go, well, we want 10% probability of being here, 90% probability of being here, or whatever, 1% here, 99% here. That can be controlled simply by driving it with microwave pulses. And then what we can do, the final piece of the puzzle, is if it is in one of those states where we've got a mixed state, so let's go back to that, go back to these, and actually let's now just turn them off. What we then can also do, simply by waiting, is just wait until those arrows are misaligned, and this will give us destructive interference. Those arrows being misaligned, remember, what does the position of that arrow represent? Well, it represents where we are on the sine curve. So if they're completely out of phase, then we get destructive interference. And that's how we do the calculation. Coming all the way back to when we looked at that modular exponentiation function, and we were building it up from different waves, different frequency waves. That's what we do. We carry out that Fourier transform process. We determine the frequencies that contribute by controlling how the waves interfere. That's what we do. I hate to say it again, and I'm just going to put the hat on just once. The physicists will know what I mean. The key thing here is you can do the bookkeeping whatever you like, but don't confuse the map with the territory. Don't confuse the model with actually what's happening in terms of reality, however we define that. If you want to couch your calculation in terms of multiple universes, that's fine, do that. Just don't pretend that there's any empirical evidence for those universes existing. So one of the difficulties with this sort of n is equal to 15 model, which we can factorize n is equal to 15 in our heads, even I can do that. One of the issues is you can sort of see the answer in advance, and that's sort of good from an educational perspective, but it also sort of takes some of the shock value, the wow value out of it a little bit. But the important thing is this: if you've got 2048 bits, right, you are not going to see that pattern. And importantly, the sequence of pulses and weights, etc., that you use to implement the Fourier transform, the Fourier processing, is exactly the same. In this case, we know the answer in advance, but it's not like we've chosen the sequence of pulses to pull out that particular answer because we know it in advance. We've just said, well, what does our quantum Fourier transform do? We apply these pulses, these wait times, these measurements. That gives us the frequency, the fundamental frequency, and therefore the period of the function. It doesn't matter if that's 4 qubits or if that's 2048, 4096, whatever qubits. It's the same process.
So basically, if we revert back to when we were looking on the screen and we were adding and seeing the little red bars pop up, we didn't know that it was 148 blah blah blah, but that came out of what we did.
Precisely. So yeah, it's exactly that. In our case, you can eyeball the function. When we did it before, you can eyeball it and see, right? But if that's 2048 bits, a 600-digit number, you're never going to be able to do that. But what will happen is when you apply the Fourier transform, you might have to, it might be a very long spectrum, but you will go, oh, there's the peak. That's the repeat frequency. And you, instead of trying every single alternative in terms of the factors, it just pops out. That's the beauty of wave interference. That's the beauty of quantum mechanics. And that's where the real speed up comes from. Instead of trying every factor by hand, out pops the period.
So perhaps one thing that's worth thinking about is how practical and realistic is this, and in what sort of timescale might we see something like this. Quantum computers at the moment, they're very noisy systems, and so you have to have lots of duplicate qubits so you can do noise reduction and all these kind of error correction. So given that, we can't realistically factor any number bigger than about 15 at the moment. And so it isn't hugely useful for a 2000-bit RSA problem. But I guess the real interesting thing is we don't know, right? We don't know when a quantum computer will be big enough to do it. It could be in 5 years, maybe more realistically 20 or 30 years. It could be hundreds of years. But perhaps we should think about this before that happens, given the impact it's going to have on all of our cryptographic algorithms.
Yeah, it's a massive engineering challenge. You've got to, because everything we've talked about is controlling the relationship of the phase of the waves, getting constructive or destructive interference, and very precisely controlling that. The problem is if it's coupled to the environment and those waves are getting sloshed around and you're adding lots of little tiny differences in phase, you wash out the quantumness essentially, and that's why so many of these quantum computing systems, it's like heroic efforts to decouple them from the environment. Ultra-high vacuum, low temperature, etc., etc., etc. Everything I've talked about has been, this is ideal. This is what we have in the idea. That's taken no account at all of error correction. And you've seen that even to factorize 15, which is a sum most people can do if they can remember their times tables, is still a massive effort when it comes to a quantum computer. Isn't quantum wonderful, though? And the other important thing to remember is everything we've talked about happened in this universe. We didn't have an infinite number of pixies in other universes doing the calculations for us. Just this universe is enough, more than enough.
I want pixies.
Okay.
The brighter it is, the higher the probability of finding the particle there. This is a quantum particle, and this tells us about the probability. So the wave is telling us about the probability of finding a particle. You can see it's just basically an intensity map of this.